All right, so we did a couple of buffer overflows on Linux, and now we're going to do the whole exploit where you take over the box. And like I say, this time you'll actually need an Intel machine because the last step currently only works for Intel, although I expect that to change pretty soon. So you do have to disable address space layout randomization, which I've already done on this machine, I think, and if not, we'll find out pretty soon. And so this time you just download some source code in a precompiled binary, which of course, if you look at, use the file command to see what it is, ed3a, that should be. This is a 32-bit Intel compiled code. So that's another reason why you need an Intel processor and you need to have that multi-library support that we installed in the last one. So you can run this thing. All right, and it tells you you have to have a string. So you can give it a string like AAAA, and then it runs with no problem. All right. And you can look at the source code, 3A, there. And so it'll tell you here, it is the main routine takes a command line argument that can be as long as you want, and then passes it to copier, here, copier argv1. And copier copies it into a buffer that only has room for 1,000 characters and then returns. So it's like the others, there is a buffer overflow, but you have to have more than 1,000 characters for the buffer overflow to take effect, which is deliberate so we have enough room there to put in a whole exploit, which takes some room, at least a few hundred bytes. So the first thing I made was a fuzzer, and all the fuzzer does is repeat A's or whatever length you tell it to run. So if I clear and run the fuzzer on 10, I guess 20 is fine. I get 20 A's, and 200, I get 200 A's, and so on. So now I can test the program by running it this way, run ed3a, and take the command line argument is going to come from the fuzzer, 1,000. Okay, and 1,000 works fine, but 1,020 overflows it and causes a segmentation fault. So now I know that somewhere in the last 20 characters is data that corrupted the instruction pointer or some other register like the base pointer. So you find out the details of what went wrong by going into the debugger. And let me make this window bigger, and I'll refer to my instructions in the other window here. On the other screen, I should say. All right, there. And now we'll run the program with the input from that fuzzer at 1020. All right. And it exited normally. It should have crashed. What have I done wrong? Oh, I am missing the dollars there. Oh, that'll do it. The pound doesn't work. The dollars is what actually runs the program inside the parentheses and puts the output in there. There we go. And now as you see, it crashes and it has 41, 41, 41 in the EIP. This notation doesn't make that obvious, but that's what it is. And you can tell by doing info registers. Here's the EIP containing 41, 41, 41. So something in the last few characters hit it. So let's get out of here and make a better program, which I should have ready. EX1. All right, so now I put in 1,000 A's, and then I put in B, C, D, E, F, non-repeating patterns, so I can tell which characters hit it. So now I can run that in the debugger. Run dollars EX1. Oh boy. Run dollars EX1. There we go. Except I'm still missing the R. Boy, having trouble typing. There we go. And so now it crashes with 45, 45, 45, 45. So that's A, B, C, D, E. It's the E's that control the instruction pointer. So now I have control of the box. And now I just need an exploit to run. And so I've installed Metasploit on this box, which is the standard open source pen testing framework you use to make malware. And you can see which malware it can make that would run on Linux. I'm going to make a bind shell, which is the simplest exploit. It is not the most powerful exploit because it's going to start a listening process on this box. And in most environments, that wouldn't work because the firewall will block incoming traffic on a strange port. So an outgoing connection, a reverse shell, is a more common attack, but this one's easier to set up and is where we're going to start. So this is just going to list all the payloads and show us the Linux ones that bind to a TCP port. And this is why we can't do it on an ARM processor. Everything works up to this point, but I can't make any working ARM shellcode from Metasploit at this point. Now, I imagine as ARM-based machines become more popular, they will update Metasploit and add those in. And then I'll be able to do all these projects entirely on ARM. All right, so there's a bunch of them. And the one I want is Linux 86 shell bind TCP, this one here. This will listen for a connection and spawn a command shell. It's just one of the simple ones. So to make the malware, if you want to learn more about the settings, you specify that as the exploit, and then you can list options to see how this one works. And it should tell us about this attack. It runs kind of slow because it's in Ruby, which is interpreted like Python. And it doesn't matter that Metasploit runs slow because it's just creating the attack, which you'll then feed in to a system that will use binary. So here's what happens. This is a normal reliability exploit on 32-bit Intel. And what it's going to do is it's going to listen on port 4444 unless you tell it some other port number. And you don't need to specify a target address because it's a listening shell. You don't need to tell it the name of the command and control server. Just anybody that connects to that port will get in the box. Another reason why this is not your most popular way to do it. And there's a bunch of advanced options that have to do with what it will do after there's a connection made, when the script starts and things like that. And I often have to adjust these to make it stop crashing on certain systems. But for this system, I don't need any of them. So I can make my malware with this command. And what this is going to do is change the local port to 31337 for no particularly good reason, and write Python code for the exploit. You can get it in many formats, and we're using Python as our exploit, so Python code is what we want. All right. And anyway, I'm not going to wait for this one. Well, yeah, I'm going to go to my instructions, might be better than waiting for it. What it's going to do is it's going to just pipe out, put us on some Python code like this. All right. Now, if you look at this Python code, though, there's a problem. Sometimes this Python code includes null bytes. And I'm not actually, there it is, there's a null byte in there. So this code would run, but only if you could inject strings, including null bytes. And since we're putting this into C processing, C strings are terminated by null bytes. So if we tried to use this one, only that much of the code would enter the system and the null byte would terminate it. So to avoid that, you have to add another parameter here, and that is this one. It turns out I had to turn on one of those fancy append exit commands to make it work. And then you encode it, and here I encode it with alpha mixed. So it'll use only letters and numbers, no special characters at all, which makes the code bigger. See, this code was only 300 bytes, and the actual contents was only 78 bytes. 78 bytes was the exploit, but this one goes up 231 bytes because it has to pack all the code and then have an unpacker in the front. So, by the way, every time you regenerate it, it will come out different because it sort of randomly chooses a key to encode it. But I've already sent you a copy of that code and put it in your exploit file, and I've already got that going. And that is, I think, EX3. Oh, no, EX2. There. So what I did was up here, just have the header to run it in Python. Then I copy the code from Metasploit, which creates this buffer. And as you can see, it's using capital A and capital B and just nice ASCII codes here. So by the way, it could, in fact, display all these as printable characters, but it just specifies them as hexadecimal codes just for generality. And then I create an attack, which is a nop sled, 500 nop commands, which are 90, which do nothing. Then I put in the buffer from here, and then I add enough of a suffix to make the total length equal to 1012, and then I put in the extended instruction pointer, which is going to go at the end, which right now I'm putting in a dummy value of 1234 because there's another step. After having this exploit, I have to figure out what address to use to run it. So let me put this one in the debugger. All right, which is GDB minus Q ED3A. Okay. And now, let me see, why did I do this with the copier? Oh, right. So now remember before, I want to have the overflow happen and then put a breakpoint in to examine it. And this time I don't have source code debugging, so I'm going to use assembly language debugging. So we'll disassemble the copier routine, which is here. And so here's where it calls string copy. That's where the overflow happens. Here's the next command. So I want to break at this address. So I'll just copy that address and then break star that address. That's how you do it to the pointer. So now I have a breakpoint at that location. So now I can run and take the data from that ex2 file I just prepared, which has the real Metasploit attack in it. And now I can examine the situation on the stack. And the registers will show that the stack goes from CCA0 to D0A8, which is about 4,000 bytes, which is 1,000 bytes, 4 pages of 256, which is what I expect. It's got a variable of 1,000 long and a few extra things there. So I can examine, say, 410 32-bit words, starting at ESP. And I remember the base pointer is D0A8. So it's going to be a couple pages long here. And D0A8 is here. So see, it injects this code, and then it puts my fake return pointer here, 1234, which means everything's working fine. I have control of this. I just don't know what value to put in there. And now I can choose a value. I just scroll back. This is the A's I put at the end. This is the code that came from Metasploit that I want to execute. So I could jump right at the start of that. But as a general practice, you don't do that. You have a NOP sled. Now, I've learned you have to give it at least 16 bytes of NOP sled, or Metasploit shellcode will often crash because it uses the first few bytes to decode it. And in general, as I mentioned, the environment is always not exactly equal to your test environment. The debugger can change things, other things can change things. Often the addresses are not exactly the same on different systems. So to make your exploit more reliable, you put in a NOP sled, and then you just jump somewhere into the middle of the NOP sled. And then even if you're off by some number of bytes, 20 or 30 bytes in this address, the exploit will still work. It'll hit the NOP sled, and it'll just slide down it, NOP, 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 and then hit the exploit, which they call the egg. So any address up here will do. I can copy that one. And so that's the address we want to inject at the end here instead of 1234. This 1234 should be that address somewhere in the NOP sled. So let me get out of here. And let's take a look. I think I've already got it set up as EX3. Yeah, and so here's the address I copied before, which led into the NOP sled. So the instruction pointer, instead of being 1234, is this address with all the bytes in reverse order, FFFFCD90. So it'll hit somewhere in the sled, slide down the sled, then execute this code from Metasploit, and that should do it. So let me, all right, I should be able to run the complete exploit in the debugger. That's one way to do it. So I can GDB minus Q ED3A. And now I can run. Now I can check it. No, I'm not going to check it. I'll just run. Okay, fine. So I can run it with $EX3. And notice now it doesn't return because it runs the exploit code. The exploit code branches a new process and starts listening on port 31337. So I'm going to leave it running here and go to another shell on the same machine and just another SSH window. And then I can just run ss -pant to see the socket states. And I see there is a process ED3A is now listening on 31337. So I can connect to it with Netcat on 31337. And you see down here, it observes that I've connected, and I can now do like who am I and uname -A. Now, I haven't really accomplished anything here. I made a shell on my own Linux machine, but this could be a remote machine somewhere. I just made it easy for students. You only need one machine to work from. But the point is now I do have control of that box. I don't have administrator control, but I have the user account that's running this program. And there are ways to escalate, and we'll see that when we get to Windows. So that's the whole process. And that's all I wanted to show you about this one. And let me just talk about the next one, which this is the basic buffer overflow, what we're doing here. And this is the origin of all the attacks. This was the original one made famous in a FRAC article by Aleph Null a while ago. This is the classic vulnerability, and all the rest are minor variations on it. By the way, if you look later in these instructions, you can, this is exploiting your own server that you set up, and then you can exploit my remote server. There's a string processor here. This is something I was real happy to figure out. You can send data to my remote server. It's hex, so I can inject, say, 41, 41, 41, 41. I'll put 8 of those, and then debug it. And now on my server, I'm just running GDB using a little script. So it shows you the pointers on my server, which go from DA40 to DF38, and then the stack at the point of the crash. So DF38 is the end of the stack frame. So this is the return pointer. You can see where it is, and you can read up here and see the contents of the stack. So you can exploit this server completely through this. You have enough information here to figure out how to do it. You can inject code until you find out how to control this value, and then you can inject a NOP-SLED and a Metasploit shellcode, and you can find addresses for the NOP-SLED and figure in one of the addresses here. You can take over my box and get a shell, and then you can go on through it and find flags on there. So this is kind of fun, and we're going to see this a lot more when we get up to later exploits. I think, in fact, it was part of ED202. I skipped over it, but I should mention it here. This one here has a bunch of these exploits. You can exploit my remote servers. I wrote this on like a 14-hour plane ride to China for DEF CON China. I realized I could practice on my local box. And so after you get it working in 32-bit, you can then use one of these remote processors to run the win function on a 32-bit machine, and then a remote 64-bit machine, and then a machine with address space layout randomization turned on, all running on remote servers. And it's nice. I realized I can just run GDB on the server. You can see all the information you need to develop your exploit. And that's good for people to practice these variations. And the last variation I think I want to mention in this class is this format string vulnerability, which is bizarre. And it's, again, a vulnerability caused by the bizarreness of the C language. So when you print something in C, you put a format string in your printing. You're supposed to have a print command. Let me bring up a text window to type into, because there's a series of slides and lectures that goes with this, which I don't have. But the right way to print something in C is printf, and then you say like a format like %d, and then you print a variable I. So that's how you would print the value of an integer variable I. And there are a bunch of these format specifiers, %d for decimal, %x for hexadecimal, %s for strings, and so on. But then there are some really, really strange ones, like %n is the worst one. What %n does is it takes the variable it was going to print, interprets it as an address, and writes to that address in memory. I don't know why they put this in there. It's completely insane. And the value it writes is equal to the number of characters that have been written so far. So I guess it's for some sort of advanced string formatting feature, but it means if I can control the format string, I can write directly into memory by address. And I can read. Now, here's another fun fact, which is a fundamental issue that applies to every operating system, including Windows. The way this is actually implemented in assembly code, let me go back and see if I can show you on my live code here. if I go back into the debugger here, let's get out of here and let's just go back to here. I'm in the debugger, in fact, right now. Let's disassemble main. All right, let's uh, just start again. All right, and now disassemble main. I'm going to main now, maybe. All right, I'm having trouble getting going here. GDB minus Q. Now maybe I can do it. Disassemble main. There we are. So what I wanted to show you is when I call a function like printf, the way it works is I push the arguments on the stack. So here it is pushing a pointer to the string to be printed, and here it's pushing a pointer to the format string, and then it calls the printf function. So the way assembly code works, the way the computer really works, is when you enter the printf function, it will just look on the stack and assume that whatever it finds on the stack are the correct parameters it should be using. It doesn't have any way to know if the programmer correctly prepared the stack or not. And that means if you make the mistake made here of just printing something without specifying the format string, and this is something the user controls, the user can insert the format string and it will fool the system. So you can run this program and you can just feed in a format string instead of feeding in a variable to print or a value to print, and then it will just reveal data from the stack. I give it set x, which is hexadecimal, and it just gives me 4 words off the stack. So this print command turns into letting me read arbitrary memory starting at the stack. And if I put in %n, I'm writing to arbitrary memory. So now all you have to do is find a way to take over the box with a write operation, and that turns out to be pretty easy to do. So the first thing is to control the parameter. So it turns out if you put in some characters and then the %x, these characters go on the stack and you can find them. So the 4th word on the stack is equal to the first 4 characters I put in. I put in 4 A's and I'll find it at the 4th word. So now I know how to put in code, and if I put a %n as the 4th format string, it will write to that memory address. So now I just need to choose a ramification to write to, and you'll see this program calls print, and then later on it calls exit to leave the program. So what I can do is I can overwrite the pointer to the exit system call. So when it tries to exit, it will instead go to an address of my choosing. And that's called the procedure linkage table, and the global offset table are these tables through which it goes. And you can use the objdump command to find the addresses. So this address 0804A014 is the pointer to exit. So I can just write to that address and it will change that pointer. Now, right now, it'll change it to a small number like 1B because it's just going to be the total number of characters that were written. But by writing more careful Python code, you can write 1 byte at a time, and then you can carefully increase the length of the printout up to like 255. So you can write, you write a 32-bit word starting at this location, but the last byte is the number you want. Then you move over 1 and write another 32-bit word where the least significant byte is the one you want, and you continue that. And after 4 write operations, you will have put in the entire 32-bit address you want, plus doing some collateral damage in the next 3 bytes that we can ignore. So you're able to write an arbitrary address in there, and I start with A, B, B, C, C, D, D until you get it right, and then you can eventually fine-tune your code until you're actually writing in the correct address. And so you repeat the whole thing. You put in an op sled, you put in an exploit. Here I'm just using interrupt commands to test it. And you can go through the same process going through the format string. So it's all very much like the buffer overflow with a few little wrinkles added in. And the same is true of all these other ones, heap overflows and so on. So I say the buffer overflow contains like 90% of what you need to know for all these exploits, and all the rest are just minor variations on it. So that's what I wanted to show you about Linux, and we'll do Windows next. Let me stop this.